Right, so the next gate that we're going to be talking about is the NAND gate. In the NAND gate, you can drive the Boolean expression with a dot and an overbar between the inputs, which can be shown as x equals to a dot b to the whole bar. And this is the symbol used for NAND, which is basically a D with a dot afterwards or an invert afterwards. And this gate, the NAND gate, is equivalent to the negative NOR gate. Right. So the truth table we can show is like this. To make it easier for you guys, we can break down the outputs and then form the complete output uh, of the NAND gate. So first we can just multiply, and then afterwards we'll invert the multi multiplied output. So the first thing that we're going to do is just basically apply the AND gate, which is 0 0 0 1, and now we're just gonna apply the NOT gate and invert our output we got from here. So 1 1 1 0, which is, this is basically what the NAND gate is. It's like a combination between two uh, basic gates, which is the AND gate and the NOT gate. So we have a question here, which is apply the NAND gate on these binary numbers, which is A equals to 11100 and B equals to 11001, and then we have to draw a truth table and a waveform too. So let's make the truth table first. Sorry, we've already made the truth table. uh, we'll just make the waveform, which is basically gonna be 1 1 1 0 0, and then we have 1 1 0 0 and 1. Right, so we'll get 1 1, which is a 0, as we're multiplying and then inverting afterwards. 1 1 is the same as this. 1 and 0, we're gonna get a 1. 0 and 0 will get a 1. 0 and 1 is gonna be a 1. Sorry. Like this. Right, so let's move on to the next gate, which is the NOR gate. The NOR gate is shown with a plus sign and an overbar between the inputs, and this is a combination between the OR gate and the NOT gate. And this gate is also equivalent to the negative NAND gate, the negative AND gate. The negative AND gate. Right, so let's make the truth table first. If we're just gonna apply the simple OR gate, which is 0 plus 0 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. Now we're just gonna invert the output we got from the OR gate, which is 1 0 0 0. So in this we can see that in the NOR gate we only have a high output when both the inputs are 0. And in the previous example, in the NAND gate, we saw that we only got one low output, which is when both the inputs are 1. It's basically the complete opposite of each other, the NAND gate and the NOR gate. So the question that we have is that we have to perform the NOR operation between these two inputs A and B, and then draw a waveform. So we'll just directly draw the waveform like this: 0 0 1 1 1 and 0, and 1 1 1 0 1 0. Okay, so uh, we're only gonna get a high output when both the inputs are 0, so we'll just find that which is over here, which is 1. The rest, all of the inputs have at least 1 in them, so it's gonna be 0 in the rest. That's just how easy we can draw the waveform with. And then the next gate that we have is the XOR gate. The XOR gate is also a combination between 3 gates, which is the AND gate, the NOT gate, and the OR gate. And this is shown between with a plus and a circle around the plus between the inputs, and we can derive the Boolean expression like with this, or the full form of this expression is a bar b plus ab bar. Right, and this is the symbol used for the XOR gate. And let's make the truth table now. So first we're gonna give the output for a bar b, then we're gonna give the output for a b bar, and then we're just gonna add these two together, or like apply the OR gate together, and that's basically just going to be the output. So this is basically the NOT gate and the AND gate together, these two, and then we're just gonna apply the OR gate here. So 0 is the first input is gonna be inverted, and we're gonna get a 1 here and a 0 here, which is still gonna stay as 0. 1 1, which is gonna be given as 1 1, and 0, which is going to be a 0. 1 and 1, we're going to invert this to 0, so we're going to get a 0 here. Right, so in this one we're going to have a 0 and a 1 because the b is inverted, so we're going to get a 0 here. 1 and 1, sorry, 1 and 0, so this is going to stay 0. 1 and 1 because it's going to be inverted, so we're going to get a 1 here. 1 and 0, we're going to get a 0. Right, so now we're just gonna add these two outputs together. We're gonna get 0 1 1 0. Now you don't really need to draw this, you can just get the direct output too, but just to explain to you guys how to get this output, I'm doing this. Right, so now let's draw the waveform for this question, a, b, and x. 1 1 1 0 1 0 1 and 1 1 0 0 1 0 0. Right, so the output we're gonna get is that if we have both of the same inputs, we're gonna have a low output, and if the inputs are opposite to each other, we're gonna get a high output. So let's look for the two opposite inputs, which is here. So there's going to be a high output here and here. You have a high output here because both the inputs are opposite to each other, and in the rest of the inputs we can see that both of them are equal to each other. They're the same, like 1 1 1 1, so it's going to be a 0 here, a low output. 0 0, which is still going to be a 0. 1 1, a 0 low output. 0 0 and a 0 low output. This is basically the waveform for these two binary numbers for the XOR gate. So we can say that a high output will be given when both inputs are opposite to each other. Right, so now let's move on to the XNOR gate. Now the difference between the XNOR and the XOR gate is that they're just opposite to each other, and we can even see this in the symbol that we use for this gate. this is basically the XOR gate here to here. Then we're just inverting the output we get with the XOR gate over here. So we can see that it's just like the complete opposite of what the XOR gate does. And we can derive a Boolean expression with x equals to a bar b bar plus ab, which is a bar multiplied by b bar plus a multiplied by b. Now let's draw the truth table. Uh, First we're gonna multiply the two inverted inputs, and then we're gonna multiply the two normal inputs, and then we're just gonna add them up together. So the two inverted inputs, we're gonna get 1 0 0 0, and then 0 0 0 and 1. Now we're just gonna add them up together, which is this. Now in this you can see that you're getting a high output when both the inputs are the same. You can see that if it's a 0 and 0 we have a high output, and if it's a 1 and 1 we have a high output. So let's make the truth table for these two binary numbers, which is 1 1 1 0 0 1 1 1 0 0 1 0. Right, so the output that we're gonna get is 1 and 1. Because the both inputs are the same, we're gonna get a high output. 1 and 1, both the inputs are the same, so a high output. 1 and 0, both inputs are opposite to each other, we're gonna get a low output. Both inputs are same here, so we're gonna get a high output. 0 and 1, opposite, low output. 1 and 0, low output, because both the inputs are opposite to each other. Now